So the title for this talk is In-Data versus Near-Data Processing, a little bit long, the case for resistive CAM processing and storage, CAM being content addressable memory. I'm not going to repeat the motivation. Shahar presented it very well. I'm just going to say that von Neumann architecture is not all that bad. It's just less efficient for a growing class of problems which share a certain amount of common characteristics. And the solution to this problem is indeed near-data processing. Our own solution is in-data rather than near-data processing. And it has two principles it relies on. The first principle is called associative processing. And the second principle is resistive content addressable memory. Now, associative processing, I see here in this audience at least 3 people who know what associative processing is. Probably nobody else knows. Associative processing performs now computations in conventional sense. Associative processor has no PUs, no ALUs, no floating point units. Associative processing is done very similarly to lookup table, just the other way around. In typical lookup table, you have the function arguments and values stored side by side, and the data comes in, matches the argument, and we pull out the result. In associative processor, we have data residing in memory, in associative memory. Function arguments come from outside, being compared against the entire data set. And wherever there's a match, we just write the result, the function value, in the result field. And I will give you a specific example of associative processing calculating sum of 2 vectors. So this is the associative memory. Has 128-bit columns and a known number of rows. There are 2 vectors, A and B, each 4-bit wide. Every element occupying 1 row. We're going to place the result S, which is A plus B, in this specific field from bit A to bit 11. And bit 12 is going to be the carry bit column, which will also hold the 5th bit of the result. Associative arithmetic is usually done in bit serial manner, meaning that we will just in hardware adders, for example, in ripple carry adder, we will first add 0 bit, then we'll go to the first bit, to the second bit, and so on. And between the bits, we will move the carry. Now, this is the function that we want to implement, specifically the truth table of full adder. It has 3 inputs, A, B, and C input, and 2 outputs, S and C out. And since it has 3 inputs, it will have 8 different entries. As I said, bit serial. So we will first mark bit 0 of vector A, bit 0 of vector B, and carry in, which is reset in the end. And we will simply go over this truth table, comparing all the combinations to the entire data. So wherever this specific combination 0, 0 is found, we mark those rows, or we tag them, rather. And wherever the row is tagged, we will write the result, which in this case is 0, 0. Then we move to the next combination, 0, 0, 1. And wherever this match is found, we write the result, which is 0, 1. And so on and so forth. I'm not going to go through the entire table. After we finish the table, we move to the second bit, meaning bit 1 of A, bit 1 of bit 1 of A, bit 1 of B, and carry in, which was the carry out of the first stage, and so on and so forth. In the end, we have the complete result stored in the field S, plus the out, which is the 5th bit of the result. This is what associative processing does. Two things worth mentioning here are associative processing is processing in memory. Ideally, we never move the bulk of data outside the memory. The second point is associative processing, at least associative arithmetic, is independent of data set size, meaning the better the problem is, the better the efficiency of the associative processing. This is not true for all cases, but true for many, many cases. We all know what resistive memory crossbar looks like. Not everybody knows, though, that to convert RRAM into ReCAM, resistive content addressable memory, all we need to do is to logically pair two memristors, two memory cells, where we write the value in, say, left cell, and the 2's complement in the right cell. The rest is exactly the same, so it's the same crossbar. Moving to the architecture. There are three main parts in this resistive architecture. The first one, of course, is the resistive content addressable memory array. All those small cells are actually double RRAM cells, so it's the same crossbar. The difference is on the sides. The row of this ReCAM is a tiny processing unit for us, and we usually keep a data element per row. The second element is this tag array or tag chain, which consists of a little memory cell, not necessarily a flip-flop, could be just SRAM memory cell, maybe resistive memory cell, which holds the result of compare to affect the write in the next cycle, plus some additional logic, which is used in some additional associative operations. For example, this OR is a part of what's called in TQAM a priority encoder, which encoder or decoder, whatever, which shows the first row which matched and ignores or resets the others. And there is another piece of circuitry which shows us that there's been at least one match in the entire array. And the third part is called reduction tree. It's used in applications where you need to reduce vector to a scalar. It allows a quick summation of tag bits, so it's a large piece of hardware, but it's optional because not in every application we need to reduce vector into scalar. Just to give you a sense, a taste of the level of scaling and integration here. So today we have 25 nanometer memristors, and I'm assuming 100 femtojoules per write, which is an aggressive figure, but at least this figure has been reported. Now, obviously, in the architecture like that, energy is dominated by write. Read is completely negligible compared to write, so that's the important piece. And assuming operating frequency of 100 megahertz, so we can squeeze 2 million PUs into a square millimeter, meaning that if we go for 500 square millimeters, we can squeeze a 1 billion PUs, which will give us the equivalent top theoretical performance of 100 teraflops, but it will dissipate 1,000 watts, meaning this impractical. So probably today we wouldn't go above maybe 10 million to 50 million PUs. However, in the future, when one of these days memristors become a 1 nanometer device, which is definitely possible if people make carbon nanotubes in 1 nanometer, so why not memristors? And if the write energy is brought down maybe 1 order of magnitude, then we can theoretically stick 10 billion PUs on a single piece of silicon, and I'm talking 2D, not 3D, which would probably enable peak theoretical performance of 1 petaflop. Again, I don't know if GPUs will ever get there in 5 or 10 years. Maybe they will, maybe they won't. To show you where we are relative to other near data processing solutions, So, and I'm showing it on an example of processing and storage. Processing in memory actually uses the same principle. So near data processing, or conventional near data processing, means just copying, replicating a little von Neumann architecture inside a storage or a memory array. So in typical SSD, you would see a number of flash channels and a little CPU core sitting on the side. Typical bandwidth in a system like that ranges from a few hundreds of megabytes per second to maybe a few gigabytes per second. If you push it, if you add 16, 18, 20, 24 channels, maybe you can go a little higher than that. That's pretty much it. So one single CPU core has no problem dealing with such bandwidth. Now, what happens if in a few short years, flash is replaced by RRAM, and due to RRAM features and internal characteristics, this throughput jumps, the bandwidth, the internal bandwidth jumps from a few gigabytes per second to a few terabytes per second. Now, obviously, one single core cannot deal with that. Now, the typical von Neumann response would be to parallelize. So there's going to be a number of PUs. Number of PUs, meaning you have to somehow connect them to storage arrays, which means there's going to be some kind of network in storage or parallel bus in storage, which means you're going to have, again, limited bandwidth, meaning you will restore, replicate von Neumann bottleneck, which you had in macro world, you will restore it, replicate it in storage or in memory processor. Now, one legitimate solution which is offered for processing in memory is 3D integration, where you have, for example, two silicon layers. First one is PUs, and the second one is memories. So you are able to use all the benefits vertical communication gives you, but still you have to go through TSVs or something similar, which again have much higher bandwidth, but still limited bandwidth. Our solution, similar to Shahar's solution is in data processing, meaning we, again, ideally never transfer our bulk of data outside the memory array, meaning we can fully benefit from huge internal bandwidth, which is enabled by resistive storage. Last part of my talk, algorithms. I said those applications which favor the near data processing, they have a number of common features. First one, of course, they have to have very large data sets. I mean, the data sets which, of course, don't fit in on-chip memory and normally don't fit in a DRAM. So you have to go to storage every time to bring a piece of data. Those workloads are massively fine-grained parallel workloads, meaning you do a similar simple operation on every piece of data, on every data sample. Low arithmetic intensity or high data intensity. Arithmetic intensity is ratio between arithmetic operations and data and memory access. So you have to have data-intensive workloads for near data processing to outperform von Neumann architecture. And something which is specific to associative in data processing, limited precision calculations, which are, for example, recently in favor in deep learning, especially in inference part, int8, or ternary or even binary calculations. One algorithm which we have implemented, and it's actually a class of algorithms, including dense matrix multiplication and sparse matrix multiplication, is called SPMV, sparse matrix by vector multiplication. It's an extremely popular machine learning kernel. If you look under the hood, probably 95% of CPU is spent on this SPMV when machine learning tasks are running. Typical CPU or GPU application has the time complexity of n and z, where n and z is number of non-zero elements in a matrix. Our in-data implementation, even a naive one, has the complexity of O of n, where n is the matrix dimension, not n squared, n, one dimension. So if I order my matrices in the order of rising n and z over n, then at the low end, at the left side, our in-data processing loses. However, as we move higher on this ratio, it becomes outperforming CPU and GPU solutions. Those are 20 matrices from University of Florida sparse matrix collection with n and z ranging from a few hundred millions to almost a billion. And in power efficiency, we also outperform existing solutions, although not by huge factor, again, because of very costly write, which we do all the time. Another algorithm which we have implemented is K-means, again, a popular machine learning algorithm used in unsupervised learning. The reason we're able to outperform GPU, CPU, and even hardware accelerators implemented in FPGA is in-data processing, meaning this algorithm is extremely memory bound, and we don't have this problem, we don't have this limitation. And the other reason is, again, fine-grained parallelism, because we do the same simple operation, calculating Euclidean distance for every sample, for every dimension, for every center. So it takes a lot of time, but when you parallelize it in associative implementation, it becomes very, very efficient. Another algorithm, K-nearest neighbors, conceptually similar to K-means. Again, we have a huge data size, and we need to calculate distances for every sample every time. So fine-grained parallelism, memory-bound application, and we are able to outperform the existing solutions both by in terms of performance and the energy. Now, this is runtime, so lower is better. The last algorithm which I'm going to cover, it's an outlier, has nothing to do with machine learning. Smith-Waterman is the most popular sequence alignment algorithm, and sequence alignment is a thing used in bioinformatics, for example, for personalized healthcare. That's an O(n) square complexity problem, and we reduce it to a linear time complexity and efficiently implement it in ReCAM-based storage, and again, compare it to existing GPU and FPGA solutions and come on top. In terms of conclusions, again, our belief is that ReCAM processing and storage might deliver next 10x improvement in performance, maybe. Because of its in-data processing capabilities, it might enable exabyte processing in the future. As Mark said, there is a huge programming challenge, programming wall, because all those algorithms that I mentioned, we have to program them manually. There are no software tools, of course, so it's a big problem. Last one, just want to recognize my partners to this research, Roman Kaplan and Ran Ginosar, and E.B. Friedman and Engen Ipek for inspiring this research, at least in its beginning. Thank you.